Hello dear students, I am Samir Velankar. I welcome all of you to this another video based on the topic properties of asymptotic notations. In the previous video, we saw some of the important properties of asymptotic notations. In this video, I will tell you two more properties of asymptotic notations. And then we will continue solving some problems on comparison of functions. Here we go. One more property of asymptotic notation. Now, before I discuss this property of asymptotic notation or theorem, we can say, let's imagine that we are given some code. I'm not writing the code, but just imagine we have got a segment here, some code written, and in the same program we have got some code to follow. Okay, some code written here above and some code after that. And we have analyzed that the code written above here is of the order of n. That means there are n computations done by this above code, and the next code which is written just in the same program, the next code is O of n square. So there are n square computations done by this particular segment, the below segment. Then we are asked what is the O notation? What will be the time complexity for the entire code? We are asked. So obviously we will say that the entire code works in On plus O of n square. Definitely we will say this, isn't it? Because they are back to back, On and On square. So total time is On plus On square, isn't it? But now we know that these two are polynomial. First one is a polynomial of degree 1 and second one is a polynomial of degree 2. So indeed, in our analysis of the above code, that means when we said that the first part of the code is On, we must have got some polynomial like 2n plus 1, whatever. But there was a polynomial of degree 1. So we discarded all the constants and multiples and we wrote On. And in the lower part of the code, where we said that performance is On square, we must have got some polynomial like 3n square plus 8, something like that. You know, when we try to actually count frequency of the occurrences or frequency of the statements, we would get some polynomial like this. And then we discarded the constants and we said that it is On square. But you tell me, if you add up all this, aren't you going to get 2n plus 1 plus 3n square plus 8? Yes, it is nothing but addition of the time complexities of both the codes. Basically, the highest term in this polynomial is n square, 3n square, isn't it? So you will discard all the constants and multiples and you will write On square. So what it means is that if, wait a minute. Okay. What it means is if we have two big O notations or two back-to-back codes, each having their own big O notation, and somebody asks us what is the overall big O notation of the entire code, then you should take maximum between the two O notations. When the two O notations get added, then the maximum function should be taken. Obviously, I proved it. If it was 2n plus 1 for the above code, 3n square plus 8 for the below code, when you are adding, the two polynomials will get added and you will obviously get n square as the highest term. So that's what has been written here. You see, if Fn is big O of Gn, so you can imagine that this part represents Fn and Fn is equal to O of n, that is Gn, and Wn, the lower part of the code, is equal to big O of n square, so that is Tn. So just check this arrow, this n denotes Gn and this n square here denotes Tn. So what will be big O of Fn plus Wn? If you add these two functions, if you add these two codes or the polynomials representing the codes, then you will get big O of n square. Maximum of Gn and Tn should be big O. Big O of maximum of Gn and Tn will be what Fn plus Wn will be. I hope you have understood. So from now onwards, you remember whenever you get back-to-back codes, whenever you get some code, and after that some more code, and these codes work in the order of, let's say, n, and this code works in the order of n log n, and you are asked that what will be the overall asymptotic notation for the entire code, then it should be O of n log n, because after all you are adding these two orders. Then the highest degree over here is not n, this is n raised to 1 hardly, but this is n raised to 1 multiplied by log n. So your asymptotic notation for this entire code will be O n log n, maximum of the two. Remember, maximum of the two functions. Okay. Now the next thing, very interesting, next property that we have is, suppose we are given two functions, fn and wn, and fn is big O of gn and wn is big O of tn. Now what if we multiply these two functions, fn functions, then what will be their order? I mean, they will be big O of which function? This will be a new function, fn into wn, because we are multiplying two functions. Then it will be big O of nothing but product of their original orders, gn and tn. Now to understand this, just imagine that we have some for loop. Let's imagine, and that for loop runs with x going from 1 to n. I am writing it in algorithmic fashion, not in C language. So x runs from 1 to n, and in this loop we have got some segment, some part, okay, which is repeated by the for. Please try to understand this, right? So now if you just check this, if you are asked what will be the overall time complexity, or what will be the overall big O notation for this entire code, then in that case you will say that this for loop repeats n times, isn't it? So it works in the order of n. Definitely it runs in the order of n, correct? But suppose inside this we had another for loop for y is equal to 1 to n, and there is some statement that you are repeating. Now you watch, this for loop is also repeating n times, so it works in the order of n. Rather, this whole segment you can say is of the order of n, isn't it? Because using frequency count method, we will see that this statement runs n times, so it will be order of n. Now you tell me what will be the overall big O notation of this entire code. It will be on into on, isn't it? Big O of n, because there is a for loop which repeats the inner for loop. So something is getting repeated n times, and what is getting repeated is there is another for loop which gets repeated n times. So what will be the overall big O notation of this? It will be the product of both functions. That means it will be on square. Come on, you definitely are understanding. If there is a nested for loop, both repeating n times, then definitely the analysis or the big O notation is going to be n square, isn't it? So that's what I said. If Fn is big O of Gn and if Wn is big O of Tn, then product of Fn and Wn will be big O of simply product of Gn and Tn. I hope you have got this. Now let's go on for solving some problems on comparison of functions. Okay. What happens is in GATE exam, many a times we are given two functions, or rather more than two functions, and the simple question asked is which function is smaller than the other function. Like we are given fn is equal to n square log n, sorry, n raised to log n, I am so sorry. So fn is n raised to log n. Now you all remember that if base of the log is not given, then you assume it is to the base 2. All logarithms are to the base 2 unless specified. So this is n raised to log n, and gn is 2 raised to square root of n. Now you are asked which of the two functions is larger, fn or gn. I have already written the answer, but it becomes so difficult whenever such complex functions are given. What happens is, a student keeps substituting the values over there. Let me take n as 3 and check what happens. Let me take n as 4 and check. Like suppose I take n as 4 and I have got a function n raised to log of n to the base 2 and another function is 2 raised to root n. Now if I substitute the value of n here, I will get 4 log of 4 to the base 2, correct? And I'll get 2 raised to root of 4. Then I'll get 4 and log of 4 to the base 2 is obviously 2. And I'll get here 2 raised to the square root of 4 is 2. So 4 square here is 16 and 2 square here is 4. So you will feel that okay, the left hand side, the fn given n raised to log n is greater than 2 raised to root n. This is what happens, isn't it? When you simply substitute the values, this is what happens. But you should not stick to only one value. You should go for some higher values also. For example, what if you take n as 40,000? 40,000 and then substitute the values and see, will it be still true? Will n raised to log n, will it be still greater than 2 raised to root n? Now it becomes confusing. I mean, it is so difficult to substitute such a big value during GATE exam especially, and with calculators are given, but still it will be very time consuming, isn't it? And then who knows, with 40,000 also you will get that fn is greater than 2 raised to root n, but you are still not sure. Then you will go for something like for 40 million or something like that, and you will keep doing this. This is so difficult, isn't it? So when it is not so obvious, by just looking at the functions, when you can't make out that which function is larger and which is smaller, then what you can do is you can use logarithms. Now, to use logarithms, you should know few properties of logarithms, isn't it so? For example, if I ask you what is log of a into b? Now, from our high school mathematics, we know that log of a into b is log a plus log b. Remember this. Or if you are asked what is log of a upon b, then it is log of a minus log of b. Okay? Or if you are asked what is log of, let's say, a raised to x, log of a raised to s, of course base is 2 always, log to the base 2, or rather it can be any base. These properties are true for any base, even if it is natural logarithm, log to the base e. So what is log of a raised to x? It is nothing but x into log of a. So this x simply comes here. These are very fundamental properties of log that you can use while proving which function is smaller and which is higher. So let's take these two functions. Now what we are given is fn is n raised to log n raised to log n to the base 2 obviously, and gn is 2 raised to square root of n, 2 raised to square root of n, isn't it? So now taking log on both sides, we will get log of n raised to log n, agreed? And here on this right hand side 2 raised to square root of n, we will get log of 2 raised to square root of n. Okay, now you just check that this which I am underlining is log of n raised to log n. So we can use this third property. I'll just number the properties, first, second and third. We can use this property, log of a raised to x is nothing but x into log of a. So this is log of n raised to log n. So this becomes log n, correct? This log n comes here. And what is remaining is log n, obviously. This portion, log n, remains. And the exponent log n comes here. So log n becomes this fn. And what we have on the right here is that we have log 2 raised to root n. So we'll get root n log 2. Now you know all the logarithms are base 2. So log 2 to the base 2 is 1, obviously. So what do you have? Log n and you have another called root n. Now, which one is higher? Now, you see, you have simplified the function a lot by taking logarithm on both sides, isn't it? You see, we were given fn, but we found log of fn, isn't it? Log of the entire function. And log of fn is this log n log n. And we found log of another function gn, which was given. And log of gn came out to be root n. So which one is larger, log n or root n? Oh, it is still confusing, isn't it? I don't know. Then what you can do is you can take log again on both sides. Now, if you take log again on both sides, you will get log of log n log n. And you know that this root n is nothing but n raised to half. Then if you take log of n raised to half, using our third property again, you will get this function to be half into log n, isn't it? Half into log n. This exponent will come here down. And on the left here, we are having log of log n log n. Now come on, you tell me which one out of these two which I am marking is smaller. It is definitely log n is definitely smaller than half into log n. This contains only log n, isn't it? So which one is smaller? Fn is smaller than gn. But initially it was so unobvious. It was not at all seen that which one is higher, isn't it? So what I did, before recording this video, I thought of taking some value of n and checking, is this true? So what I did, I think, wait a minute, I'll just check. I have got the calculator on here. Yes, let me check. Uh, yeah, I think I took uh, 2 raised to 20. N as 2 raised to 20 I took. Just check this. Assume for this exercise, oh no, not this exercise. This was what we were solving. Assume that, assume that n is 2 raised to 20. Very large value of n I am taking. Then fn is nothing but n raised to log n. So 2 raised to 20 raised to log of 2 raised to 20. I hope you are understanding. N raised to log n. And what is gn? Gn is simply 2 raised to square root of 2 raised to 20. I hope you got this, isn't it? So now I am not going to take log, because now I have got the values. I have actually taken the value of n, isn't it? Now you just check this exponent here. This is log of 2 raised to 20. Now you know log of a raised to x is nothing but x into log of a. So what we will get here is 2 raised to 20, and this 20 will come down here. This will be 20 into log 2, 20 into log of 2 to the base 2. And log of 2 to the base 2 is simply 1. So this fn becomes 2 raised to 20 raised to 20. Agreed? Okay. And what does gn become? Let's write gn again. Gn was raised to square root of 2 raised to 20, isn't it? This is what was gn, and I actually found it by using calculator. Wait a minute, I'll just erase a few things. This left hand side becomes 2 raised to 40, 20 into 20, isn't it? And the right hand side becomes 2 raised to square root of 2 raised to 20. Now it is quite obvious. You can see that this is square root of 2 raised to 20. This will be very large value, isn't it? For instance, I went to the calculator and I found out that that 2 raised to 20, 2 raised to 20 is such a large number, and so that number will be appearing here, square root of that very large number, isn't it? So we are going to get such a big number. And then we are finding square root of 1048576. Now, if you find square root of this is, oh good lord, this is going to be 1024. That means in here, we are going to get 2 raised to, we are going to get this as 2 raised to 1024, and the left hand side function is 2 raised to 40. So definitely Fn is less than Gn. Warning, if you take small values of n, you will get opposite answer. You will get Fn is greater than Gn, and then you will get misled. You will say that okay, Fn is greater than Gn, but you convey yourselves that you don't stop with very small values of n, test it with very large values of n. But anyway, you know that you should not work with large values of n in the GATE exam. You can easily take log on both sides and you can find out which function is smaller or larger. Let's see very fast now some other examples here. Here we go. Now, in the second example, we have got first function as n raised to 2 log n, n raised to 2 log n. And the second function is n into log of n raised to 10, correct or not? Again, it is not becoming obvious that which function is smaller or higher, isn't it? So I'll take log on both sides. If I take log of this entire thing, and if I take log of this entire thing, now you just check, this is log of n raised to 2 log n, isn't it? So you know that the exponent will come down. So we will have 2 log n and then log n will remain. This log n will remain here, isn't it? The exponent will come down. And what about the other function? Now you see this is log of n into log n raised to 10, isn't it? Log n into log of n raised to 10. So you know log of a into b is log of a plus log of b. So the other part becomes log of n plus log of log n raised to 10. I hope you are understanding, isn't it? This is a into b here, log of a into b. So just add the logarithms of a and b. So let's keep this left hand side as it is, 2 log n, and the right hand side is log n plus. Now you see this 10 will come down here. This is exponent. So 10 log n. This is log n. 10 comes down there, isn't it? Now check which function is higher or smaller. Now this left hand side is 2 log n, and the right hand side contains a lone term called log n. Log n added with something. Agreed, this is 10 log n, isn't it? Which one is smaller? What do you think? Obviously, the left hand side is smaller because there is log n added with something and left hand side contains 2 log n. So I hope you are understanding. I hope you are understanding that definitely Fn is smaller than Gn, isn't it? So I think I wrote it wrong here. Answer is Fn is definitely smaller than Gn. I hope you are understanding this. Yes, everyone. So now let's see the next example. Here we have 2 raised to log n. Other example. Now Fn is 2 raised to log n. So we have 2 raised to log n, and Gn is n raised to square root of n. Well, we are not sure which one is larger. Take log on both sides. Now we have log n, this exponent comes down into log 2. And we here have this exponent root n comes down, root n, and we have log n. This log n remains here, isn't it? But you know log 2 to the base 2 is 1. So we have log n, and the other person remaining is root n log n. Come on, which one is higher here? The higher function over here is definitely root n log n, isn't it? That means log n is smaller because the left hand side contains only log n and the right hand side contains log n multiplied by root n. So definitely Fn is smaller than Gn, correct or not? I hope you got this. Let's take one more function. This seems to be quite complicated, or no? Now it won't be, I think. Now the fn given here is 3 into n raised to square root of n. Check this. And gn given is 2 raised to square root of n into log n. Now it's asked which one is larger. So it's better that we take log on both sides. If we take log on both sides, this will be log of 3 n raised to root n, and this will be log of 2 raised to root n into log n. Now you tell me, isn't this a into b? Isn't it? This is nothing but a into b. So you can say this is log 3 plus log of n root n. This becomes the first part. And the other part, now this is log of a raised to x, a raised to x. So this becomes root n log n into log 2 to the base 2. But log 2 to the base 2 is 1. Now log 3 to the base 2 is something like 1 point something. Let's say 1.5. It may not be 1.5, but it will be somewhat higher than 1, plus log of n raised to root n. And what remains here is root n log n. Okay. Now still confused. Which one is higher and which one is smaller? Then what you can do is, well, you can take log again on both sides, isn't it? You can take log on both sides. But this is becoming bit complicated for us, isn't it so? So it's so important to remember a few properties of of logarithms, and that will become very, very helpful as we proceed solving more such examples. Now, but then, by the way, what if you take log on both sides over here again? Then if you take log on both sides, you will get log of 1.5 plus log of n raised to root n, and you will get log of root n plus log of log n. I have directly written this because this is a into b, isn't it? When you take log, they get added, isn't it so? So log of 1.5, let's keep it as it is. Log of 1.5, it will be a very small value, plus this will be root n log n. This exponent will come down, and the other part will become, this is log of root n, correct? Log of root n is nothing but log of n raised to half. So this will be half log n plus log of log n. Now it becomes quite easy to compare these two functions, isn't it? Now on the left hand side, we have got root n log n, and on the right hand side, we have got half log n, isn't it? Half into log n, but this is root of log n, root n into log n. Tell me which one will be higher over here? Just check yourselves. Which one will be higher? Come on, this is square root of n multiplied by log n. Square root of n multiplied by log n, and on the other side you are having half log n. That means this is always going to get, this log n is going to get multiplied always by 0.5. But this log n on the left is going to be multiplied with root n, which can be higher for high values of n. So definitely fn is greater than gn. I hope you are understanding, isn't it? So it is so important, to remember the properties of logarithm. When you are comparing the functions, it becomes very easy. Check the answer to this question is definitely fn is greater than gn. Now, just for fun, I have introduced this example. It is so easy. Fn is smaller than gn here, isn't it? Because 2n is always less than 3n. Now, let's see one more example. Fn given is 2 raised to n. Just a minute. 2 raised to n. And the other function is 2 raised to 2n. Now, which one is higher here? Oh, it is very easy to see that obviously Fn is smaller than Gn, correct or not? because 2 raised to n will be smaller than 2 raised to 2n. But still, if you take log on both sides, you will get log 2 raised to n and you will get log 2 raised to 2n. Using our property, the exponent comes down, isn't it? So you will have n log of 2 to the base 2 and you will have 2n log of 2 to the base 2. Anyway, log of 2 to the base 2 is 1. So you have n and you have 2n. Definitely n is less than 2n. So fn is less than gn, isn't it? More examples like gate questions I will come up with on this comparison of functions and which will be thoroughly interesting. But I feel that you will find it very easy now after solving so many examples on comparison of functions. Thank you very much.